So this is the second part of a two-part symposium on infrastructures of knowledge in the Anthropocene, and really the theme of reason, space, and technology is to really acknowledge that the way that knowledge has been reorganized in the 21st century is due to a number of different factors, but in particular the interest that we have in the way digital technologies have transformed spaces and the way that we produce knowledge in the world. And so we brought together two really different but amazing scholars who are working on this question in different ways. Last night we had a really brilliant and provocative talk by Bernard Stiegler, who's visiting us from Paris, where he directs the Institut de Recherche et d'Innovation at the Pompidou Center. And tonight we're really pleased to have Paul Edwards, who is a professor of information at the University of Michigan. So before we start, I just want to acknowledge all the support that we had to put together this event. First of all, the Townsend Center was really important for that, as well as the Dean of the Arts and Humanities, and of course the Berkeley Center for New Media for hosting the event here today, and also for a lot of logistical support. So thanks to Lara and Nicholas de Monchot, the director of the Berkeley Center for New Media, and the rhetoric department as well, which is my department. So Paul Edwards, as I said, is professor of communication. Many of you know that he is from the Bay Area, a longtime resident here, where he did a PhD in Santa Cruz with the History of Consciousness program there, and then taught at Stanford for many years. His first book was the really groundbreaking, influential work on the history of computing and its relationship with military infrastructures in the US Cold War period, the closed world, computers and the politics of discourse in Cold War America. That was from 1996. His most recent work was an intervention around climate science, the 2010 MIT book, A Vast Machine, Computer Models, Climate Science, Climate Data, and the Politics of Global Warming. So you can see all of his work is invested in the relationship of politics, technology, and discourse, but also the science of modeling the world, basically, I would argue. So his newest work is around infrastructure, where he's working with some other people on a book series in that domain with MIT, and I think a new project on digital infrastructure in particular. So please join me in welcoming Paul Edwards.
Thanks, David, and everybody else. It's such a pleasure to be back in California, and especially here at Berkeley on a nice rainy day. How much you need that. So, I've got a lot here, and I hope you'll bear with me. I usually try to keep my talks to 45 minutes, but this one might go for 55 or even an hour, and we'll see. If you start to look tired, I will close it up. So, let me put a definition on the table before we go anywhere else, because the word infrastructure is a very fuzzy word and gets used in all kinds of ways, and I don't intend to try to lock it down, but this is what I mean by it. So, everyone knows what an infrastructure is in the physical sense, electric power and sewers and so on. With respect, part of the point about the idea of infrastructure is that there are things that you can rely on without thinking about them very much, because they work most of the time. So knowledge infrastructure, for me, is analogous to that, something that is made of, just like physical infrastructure, of people and equipment and institutions. But it exists to create and share and maintain specific kinds of knowledge, and I'll say more about what that means in a minute. There are lots of these things, but at the global scale, there are not all that many. And so we'll come back to that. But things like numbers for the census, people just take those for granted. They are generated, they are modeled, their data are collected. Many things happen to them before those final numbers come out, and yet mostly the numbers are uncontroversial. Weather forecasts are like that too. They're more uncertain, and people like to criticize weather forecasting, but it actually works pretty well. If you look at the forecast and it says it's going to rain, you're probably going to carry an umbrella. It might not rain, but mostly it will do something like it says. So, with that definition on the table, here's what I'm going to do today. I'm first going to talk about this idea of the Great Acceleration, which is a theme in the literature on the Anthropocene from science. And then I'll talk about this recent kind of related concept of the Technosphere, which is a metabolic process that is global in scale and consumes energy and materials and creates a lot of waste. Then we'll look at knowledge about the Anthropocene and where it comes from, and I'll try to give you a sense of a structure for that. And then some of the paradigms that have existed in the past and have become new ones that have been coming in over especially the last couple of decades. And then finally I'll talk about the idea of data exhaust, information metabolism, and our ability to recycle information to maybe get a little bit better at handling all these problems. So, the Great Acceleration. I mean, you've all seen these graphs. If you're here, you probably know what the Anthropocene is, so I will not belabor the point, but essentially it's the concept that we are now a geological force. We operate on a global scale. We affect the entire planet. Obviously true of climate change, but there are many other arenas where that's also true. The oceans, the biosphere, and everything else. The Great Acceleration idea comes from looking at the trends in many, many variables, environmental variables, over the last couple of hundred years and seeing an acceleration, mostly in the decades since 1950. Of course, this started with the Industrial Revolution, but it's been growing and growing. So these are physical variables, Earth system trends like carbon dioxide, methane, ocean acidification. But the same thing can be said of some kinds of socioeconomic variables, urban population, energy use, fertilizer consumption, and so on. Rapid acceleration post-1950, obviously related to population growth, but also, of course, connected to the growth in technical systems worldwide. So, boiling it down to one graph, it kind of looks like this, with this break point at 1950. So the idea of the Anthropocene is that it's a geological epoch, and there is now a particular moment associated with the transition, which is this, the first atomic bomb test at Alamogordo in New Mexico in 1945. So we have the most precise date ever in the history of geology for the beginning of an epoch, down to the second. This is debated. There are people who want to put it at the beginning of the Industrial Revolution, or even much further back at the beginning of agriculture, but this is a pretty convincing moment because it is easy to see that influence in the geostratigraphic record. What that means is that 100 years in the future, 1,000,000 years in the future even, geologists might be digging down through rock layers and they would come to this layer where there is radioactive dust artificially created by us everywhere in the world. The phase of atmospheric nuclear testing spread that everywhere, and it will remain visible in the rock layers for many, many, many millennia. So that brings us to the idea of technometabolism. And this is an interesting thing because it's something that STS people have resisted and spent a lot of time actually working against, the idea of a kind of technological determinism. The concept comes from an environmental scientist named Peter Half at Duke University. You can find these papers quite easily if you just look up the phrase Technosphere. But his idea is that it's analogous to the biosphere, to the atmosphere, to the lithosphere. It is something that is global in scope, that consumes energy, materials, and transforms them, and then creates waste. For him, it's not, the problem with this phrase is that people often just kind of instantly go to technology. They think we're just talking about machines and devices. But for Half, people are part of this. And he'll say things like, if you see a major infrastructure fail, you will also immediately see a swarm of activity that involves both people and devices, information systems and machines, work to repair it. It's like an organism. It seeks to survive, it seeks to grow, it continues to seek new sources of energy, and if it is attacked, it defends itself. So again, this has been criticized a lot by STS people, and in the context where I usually talk about it, that always happens. Somebody will say, but we can control it. And Half's notion is not that that's not possible, but that if we take its own point of view, rather than our point of view on it, it looks like something that has an agency of its own. So let me give you just a little taste of what this looks like as a knowledge system. This is a map of net primary production. So that's all the plant matter in the world that grows up every year and is either harvested or dies and decays and is replaced. And this is the percentage of that that is appropriated by people in different parts of the world. So you have to think of this as being, again, a system thing. There are people doing this, growing crops, harvesting them, and so on. But there are also a lot of machines and energy systems involved in making this happen. And you see that there are places like this area where I live, or India, or this parts of Eastern Europe, where almost all of the plant matter that is generated each year is taken up by people. So this includes things like land use induced productivity changes, where we just pave it over or something like that. That's about 40% of it. 53% of it is harvesting, and another 7% is human induced fires. So that's the Technosphere at work, and we can map this, we can see it develop over time, and we can see the influence of it on our own lives. This is the iPhone, basically. So these are coltan miners. They're artisanal miners digging up rare earths. It gets put into chips and made into phones, and we use them, including me. And then eventually we get waste that Jenna can tell us about later. And these devices are discarded, and some of them are recycled, but many of them are, many parts that are not reusable are just burned. Everybody knows about processes like this, and the Technosphere concept is that there are so many of these happening that we can see it as a systemic effect. There's another kind of great acceleration happening that is really worth thinking about, and that's the acceleration in the growth of human knowledge. If we take publication as a crummy but somewhat reliable proxy for knowledge, the publication rate, the output rate of science, doubles about every 8 or 10 years. And that's been true for a couple of centuries at this point. If we think about information just as a raw quantity, there are many ways of quantifying this. None of them are very good, but it's still a trend that clearly visible. We go from a world of analog information in the 80s to a world of mostly digital information, and we get there at an exponential rate. So we go from 2.6 exabytes by this estimate in 1986 to 295 exabytes in 2007, a period of about 20 years, as a compound growth rate of 39% a year. We could think about the metabolism of the Technosphere as involving information. That's one of the things that it generates and also uses. So it metabolizes it, and that is a literal term. If cloud computing were a country, it would be the 6th largest consumer of energy in the world. And that there's an enormous rate of growth associated with the internet and other digital devices. Nobody really has a great idea of how to stop. Changing subjects. Let me talk about how we know all this. So, part of what's interesting about those graphs, the great acceleration graphs, is that they themselves reflect that great acceleration I just talked about. We would not have that knowledge of all those trends without lots of studying, lots of monitoring, lots of modeling, and lots of memory. So, you know, in my book about climate change and climate science, I talked about, the title of it comes from this quote from John Ruskin in 1839, who says, "The meteorological society wishes to be the central point, the moving power of a vast machine, a kind of panoptic system that can observe the whole planet at all times, every point on the Earth's surface." In 1839, that was a fantasy. But today, it's a reality, and not just in the atmosphere. This is a map that, I know it's not that easy to see, but you're basically looking down on the planet from the North Pole in this image. And we can see, you know, here is Asia and Europe, and down here is North America. You see, already in 1914, they are drawing weather maps, synoptic maps of the pressure system of the whole northern hemisphere. Now, scientists of that time were often quite critical of maps like this because there's actually very little data in it. They drew the curves, but we don't really know what's happening between the very sparse data points on the map. And yet, you can see that it looks very much like a modern weather map. In the mid-19th century, weather surface stations started to be built in a more or less standardized way. Standardization improved across the course of the 20th century, and more stations were built, so that by 1900, most of the northern hemisphere is sort of well covered by weather stations. I mean, these rings have a radius of 1,200 kilometers, so it's really quite coarse, but nonetheless, there is a lot of observing going on. By 1960, all the land masses of the world are covered with weather stations, and that's where our knowledge comes from this monitoring system. By the 1920s, the equations for calculating the motions of the atmosphere were known. Still the same equations being used today. And the notion of modeling the atmosphere numerically was in the works. This is a more recent graphic, but the idea of this was published in 1922, actually conceived during the First World War by this guy, Louis Richardson. He created a whole set of computing forms that human beings were going to use with calculators to calculate the motion of the atmosphere. And his fantasy was that if you had enough people, you could calculate the weather about as fast as it actually happened. And this is a diagram of his vision of how you would do that with human calculators. So these are people. Each one is representing a little piece of the atmosphere. This person in the center is a kind of conductor with a colored light who's waving them around and saying, you're falling behind, go faster, or you need to slow down over there, so that to keep the calculations all coordinated. And there would be 64,000 people in this kind of gigantic spherical stadium representing the atmosphere. And with that many people, he thought maybe we could do it about as fast as the weather actually happens. That system, he tried the calculation himself. He used his own paper forms to do a calculation for a single 8-hour period over Central Europe for just this one time step of a transition. And the calculation was wildly wrong because of numerical problems that he did not know about then. No one knew about. And in fact, it was attempts to calculate the weather in exactly this way that led to a great deal of advance in the numerical methods for calculating anything involving calculus. So modern weather and climate models work more or less the same way as Richardson describes them. They divide the atmosphere up into a set of grid boxes. They calculate the transitions of mass and energy and momentum from one box to another on a time step, typically 5 to 10 minutes in a modern model. So they're doing that for millions of grid boxes. And of course, very, very rapidly in a computer. Without a computer, you couldn't really do this, so it had to wait for digital computers in the 50s to make this possible. Operational weather forecasting using computers started in 1955. It wasn't very good. It was mostly supplemented by people to make the forecasts more accurate. But today, more than 90% of all forecasts are just purely computer generated without a lot of intervention by people. There's still some situations where human judgment comes in, but a lot of it is just the models. The interesting thing about this from a kind of knowledge perspective is that, going back to the weather stations are not placed on a regular grid all over the globe, and that it's not really possible to do that. So if you're going to use a gridded model that needs data at every grid point, you have to generate that data, you have to create it. And in fact, in modern weather models, most of the data is generated from the previous forecast and not sucked in from instruments. I could talk about that for a long time, but I'm just going to move on in the interest of time. So part of what's going on in climate modeling is that over time, more and more processes have been added to the simulations. So in the early days of climate modeling in the 70s, mostly carbon dioxide, radiation, and rain. By the time of the IPCC, the first IPCC report in 1990, they had added clouds and an ocean, but just like a slab ocean, as if it were only a few feet thick, and just to get the sea surface temperature into the model. Today, there's a circulating ocean, there are aerosols, there are all kinds of chemistry cycles in the atmosphere, and many, many other things. So the system that developed in atmospheric science was a combination of monitoring systems, simulation models, and memory, which we'll come back to. Memory meaning the records of all the previous states that are generated by each day's weather observations. And today it looks something like this, with thousands and thousands of instruments on land, in space, at sea, under the surface of the ocean, all over the world. Huge computers that suck in all that data and process it with simulations. And then the forecasts are delivered to the National Weather Services, which may make further data products of their own and send them on to users of all kinds. It's an extremely important system. It's also one of the most cost-effective scientific interventions in the history of the world, because it doesn't cost very much to do this, but the amount of money that it saves in things like lost crops due to unexpected rain is enormous. So the last piece of it, as I said, is memory, and this is the storage of weather data. Today, people think of data as something electronic. It's just it's almost non-material thing, but of course it isn't. This is the entrance hall of the National Weather Records Center in Asheville in the 1950s, where there were billions of punch cards. So there were so many cards, they ran out of storage space. These are boxes of these punch cards stored in the front hall because there's nowhere else to put them. They actually began to worry seriously that the building would collapse under the weight of all these cards. So computers for them came along just in time to, not computers, but magnetic storage, came along just in time to save them from that architectural fate. Today, of course, these things are mostly stored on things like magnetic tape or disk. There's a tape robot at the National Center for Atmospheric Research. It can hold 160 petabytes of data. Almost all the things that they call data that are stored here are actually the results of simulations. Historical weather records are really quite small, tiny, compared to the simulation results that are mostly what's stored here. What this all adds up to this is the history of our climate over the last 135 years. All observations. This is not simulation. And when it's displayed this way, really fast, you can literally see the climate change, especially after the 1970s. So these three things, monitoring, modeling, and memory, are what makes up the knowledge infrastructure that brings us climate knowledge. Boiling it down to a few graphs, we can look at things like the observations, the memory, versus the simulations, the climate models. What you see in this graph is the black line is the average of global observations. The yellow lines are many, many model runs, simulation runs of models attempting to reproduce the 20th century climate just from data that is, sorry, let me say that a different way. They're attempting to reproduce the 20th century climate using the inputs that actually occurred of greenhouse gases and other human factors. So they bounce around. They do not reproduce the climate exactly. If they did that, you would know that they were wrong because the models are chaotic and the system is chaotic, so it shouldn't reproduce it exactly. But the red line is the average of all these models in one experiment. And you can see that it tracks the historical record pretty well. Now the other thing we can do with this is compare the observations against simulations of what the world would have been like if we hadn't put all those greenhouse gases into the atmosphere. So this is really the only way we can get a kind of laboratory experiment, control Earth, against which we compare the experiment that we're involved in. And what you see, so down here, same thing, black line is observations, red line is the model average. This time, without the greenhouse gases, without the aerosols, without any of the other human influences. And you see that, in the first part of the 20th century, they're pretty similar. But starting in the 60s, they diverge quite a bit, and by our time, there's no model that is reaching the same level as the observations. They just can't reproduce it without the human inputs. Yes?
How far ahead are the simulations looking?
Far. I mean, in a way, there's not that much point in looking behind. 2100 even is crazy because we don't really know what will happen between now and then. But these are a number of different scenarios for what human emissions might look like over the next 80 years or so. This part is the historical observations, and these are the main lines of the model trends for different scenarios. The blue one is the most optimistic, in which we switch over to renewables really fast, and reduce a lot of the land use change, and reforest a lot, and things like that. And then this one is where we're heading right now. This is a business as usual scenario. So, it's a fascinating, as a knowledge system, it's a fascinating thing because it does these things for us. It lets us create an Earth as if we were here, the control Earth, or any other kind of Earth. And there are actually lots of experiments that try things like, what happens if you move the continents into different positions than they are now? There are, and of course they also let us simulate our future. That's why they're so important. These experiments here are done to try to, there is no way to prove that a climate model is perfectly accurate, and none of them are. They all have biases, they all have problems of different sorts. And yet, on average, they do pretty well at reproducing what has actually happened. So let's think about this in terms of a knowledge infrastructure, something that produces steady, reliable knowledge that we can actually use. Like I said, there are other things like this, and we can see how that develops through a whole series of similar things. So the nuclear weapons testing that was done in the atmosphere in the 50s was obviously a terrible idea, but they didn't, the nuclear people didn't want to stop until they could be sure that the other side would also stop. And during the Cold War, the fact that Russia was the USSR was a very secretive place and hard to get good information out of, didn't obviously want US spies on its territory and so on. So it wasn't until technical systems were developed that could detect nuclear tests anywhere that the US was willing to go along with a test, and the USSR were both willing to go along with a test ban treaty. So, in a lot of ways, the nuclear weapons, the limited test ban treaty that banned nuclear testing in the atmosphere in 1963 was the first global environmental treaty. So what it was doing was keeping fallout out of the atmosphere. Didn't stop them from testing, they did that underground, but at least it kept it from spreading all over the place. Now the system that was developed then for monitoring all this still exists, and now it's part of this thing called the Comprehensive Test Ban Treaty. This is the, when the Fukushima Daiichi accident happened a few years ago, this is a simulation that was made by the Comprehensive Test Ban Treaty Organization of the radiation plume. Now, it was based on just some rather sketchy information that came out in the first couple of days after the accident. This is a simulation from March 18th, but it was created on March 16th. So it's what's going to happen over the next few days. Here is the CTBTO data-based simulation of that same event. So this is after the fact, when all these radiation monitoring stations that are out there for precisely this purpose, to detect nuclear tests, are now detecting radiation in lots of places and calculating how much there is and where it's going. So you can see that it's using that same system I talked about, monitoring, modeling, memory. Same thing with the Montreal Protocol on ozone depletion. We get lots of understanding of what chlorofluorocarbons are doing to the ozone layer. There's a ban, but it's not enough. And so the treaty is adjusted over a number of years based on data as it comes in. Another paradigm, and the one I'm most familiar with, maybe the biggest one ever, is this Intergovernmental Panel on Climate Change. It's not a research organization, it's a knowledge assessment organization. It takes the peer-reviewed scientific literature, and every few years they do an assessment of the quality of that knowledge and what it says. It's a gigantic thing. There are more than 2,500 scientists involved in it, many meetings, lots of digestion of scientific literature and writing synthesis, lots of model experiments like the ones I just showed you, all leading up to a kind of generalized assessment of what we know about climate change and what its effects on people and the environment are now and what they're likely to be in the future. Now, that system just keeps growing. People keep trying to do more and more with models, often by simplifying the models so that they can be combined into lots of different, to simulate lots of different sectors, not just the climate, but the biosphere, the energy sector, the economy, and so on. And they just keep getting bigger. And so this is a colleague of mine at the British Atmospheric Data Center made this slide, which modeling starts with the physical environment, then it heads into the Earth system, and then it tries to combine policy models too. In a lot of ways, it's very messy, very imprecise. You have lots of numbers coming in that may or may not be meaningful, and it's really hard to evaluate as you get more complicated. But on the other hand, what else would you do? And that's kind of the state of things around the turn of the 20th century. We even get this thing called a sort of meta-infrastructure, the Global Earth Observation System of Systems, that takes in from the air, from the space, from the ice, from the ocean, and provides data for all kinds of uses in all kinds of ways. So this has been the fundamental paradigm of how we will know about the state of the global environment since the beginning of the 20th century. Now let's look at some recycling. So recycling is, of course, a very old idea, and mostly was practiced by agricultural societies from the beginning of time. You recycle animal manure, you recycle all kinds of waste because there just isn't a lot of surplus. And this is kind of World War II era versions of recycling. we're all familiar with the recycling of stuff. Today, this is often outsourced to the third world. These are garbage pickers. This is shipbreaking in Bangladesh. We have enormous systems for doing this, but often they're invisible to the people who create most of the waste because the waste is sent somewhere else to be processed. Pretty sight. Now let's come back to information. So there's this idea of data exhaust floating around, great phrase. It's not really a recent idea. Shoshana Zuboff came up with something sort of similar toward the end of the 1980s, the concept of informating. And she was looking at factories and other places where new information systems were being added to formerly human-controlled systems, and seeing that every time that happened, they would also generate information of their own, specifically about what the people using them were doing. And that was often used for kind of surveillance of workers and to try to push their productivity, but also to optimize the whole system to work better. In 2001, this was labeled exo-information, and this is really kind of the form that we think about it today. Google, of course, works because it takes the results of everybody's searches and applies them to your search. So when you search, you are adding more data to Google's database. You don't think about it that way, but that's how it gets everything it gets. So what could we do with this idea? This part of this talk starts to sound like I'm some kind of cheerleader for corporate practices, and I don't like that very much, but I actually think it's quite important to notice where things are actually being improved using information systems, and this is one of them. So any entity that has to do a lot of transporting is using a lot of energy and would rather use less, just because it would be cheaper to use less. So there are vast information systems devoted to optimizing these processes, and they do it by monitoring, modeling, and memory. IKEA is an example. There's a lot of emphasis in IKEA on trying to create a circular economy in which you start with recycled materials and design new products that can easily be recycled, create methods for collecting the waste once it becomes waste, and then putting it back into the chain so that it kind of just circles around instead of being produced from scratch every time. UPS is an interesting example of this. UPS has 100,000 vehicles. It is the 9th largest airline in the world. And since the early 2000s, they have been using a system of what they call telematics on their trucks. So they put sensors on their trucks, more than 200 sensors all over the vehicle. Some of them are for sensing what the driver does. Some of them are for sensing what the engine and the brakes and other elements of the truck do. And they just kind of use the data that come out of that to change the trucks and also to change the drivers. It's very much the informating process that Zuboff described. They will tell them, you're accelerating too much, you're going too quickly, you're braking too hard, things like that. And so they use that to optimize the driver behavior. They also will do things like optimize routing by eliminating left turns, which take more time, but also use more gas, because you're sitting there at waiting to turn before you're able to do it across a lane of traffic. So I've been teaching for a couple of years. I taught a class on climate change informatics with a climate science colleague. And it was a fascinating thing to do. So we had informatics students and climate science students. We brought them together. The climate science students knew a lot about climate data. The informatics students know a lot about how to process data. And they really could not communicate very well. Our first task for these people was to go and just download some data from the Earth system grid, which is a giant data storage, kind of distributed data storage system. Supposed to be open access, supposed to be easy to get. 2 of the climate science students out of 20 who had experience with this before succeeded in downloading. Nobody else did. They all failed. It was too hard. Why is that? Well, partly it's just siloing. If you're already an expert on climate data, you find it easy because you have had experience with it in the past. If you're new to it, it's going to be a more complicated problem. So thinking of data and knowledge as a kind of supply chain problem, there are many gaps in it that exist because of kind of interfaces between different areas of knowledge. During the first iteration of that class, the government released this thing called the climate.data.gov, government climate data. There are lots of data out there, and this beautiful interface makes it look quite easy to get data. And in a certain sense it is. It will tell you what the format is, and you can just kind of click a button. But once you click the button, you're sent to a different website, which is the website of whatever organization created the data in the first place. So they're all different. There's no uniformity to the interfaces, or to the process, or to the data sources themselves. And once you get past this kind of top-level catalog, it all becomes quickly very confusing. One of the things that people at University of Michigan have been working on is this idea of downscaling climate knowledge. So I think I've left out a few pieces here, but the idea is the systems that developed in the 20th century were mostly global in scope and oriented toward producing global kinds of knowledge. Surprisingly, that is a lot easier to do than it is to produce local knowledge. So when I first started interviewing climate scientists, one of the ocean modelers said to me, climate models will become really effective when the grid scales reach the size of a congressional district. And I think that's really right. Nobody cares about the global climate. Everybody cares about the climate where they are. My community, my constituents, my family, people I know, places I travel. That's what matters to you. And getting this kind of global knowledge to matter to people means that we have to make that translation somehow. So this is one system that people we've worked with have been doing. So this is where I live in Ann Arbor, and the region around it. We have data about the climate of that region. What this system will do is match your community with other communities elsewhere, which currently have the climate that you will have in 20 or 30 years. So they show you an analog. Michigan, Ann Arbor, in 20 or 30 years is going to have the climate of St. Louis, or these parts of the Appalachians, or Washington, D.C. If you've been to Washington, D.C. in the summer, you will not be looking forward to having that climate. Here's another version of that this is just one of a billion infographics. I start to see these coming out, especially around the California drought, so I'm sure you've seen millions of them. Trying to really reduce these very large-scale data to something that actually matters to an individual person, like this hamburger. Now, are these numbers accurate? I have no idea, and I don't know how you verify them. But they at least have the virtue of giving you some order of magnitude take on what your impact is every time you eat a burger. Here's another really interesting example of using data exhaust, and this is not an environmental example, but I think it's one of the most interesting ones. So, Google Flu Trends. Started in 2008. They worked on it for a few years, and what they did with it was they took this period. So people are searching on terms related to the flu. Where do I get a flu shot? I think I have flu symptoms, things like that. And they're doing lots and lots of searches. So they take all those searches and they use this long period, about 5 years, as training data. And then they make an algorithm that will try to predict what will happen. and they verify the algorithm against this period of time. So what they're fitting their, the way they're verifying is they're using the CDC's actual doctor reports of flu cases. So they have kind of what we would call ground truth. They have the doctors have said, here's a person with the flu, millions of them in different places at different times. Those reports take about 3 weeks to reach the CDC, and the problem with it, with using that system to predict, is it's too slow. The flu moves faster than that, so you need something that can produce, it's like the weather. If you had a weather forecast that that couldn't be created for 3 weeks, it wouldn't be very much use. Same thing with the flu. So they make this this system, and for a couple of years it works pretty well, and they're really satisfied. This is the Chris Anderson end of theory thing. We're going to have, we don't need a theory anymore, we just need to be fitting curves. Well, the problem is that the algorithm stopped working in 2013. So here it is, tracking pretty well, and then here we come along to 2013, and the CDC says this, and Google says that. So something's wrong with it, but because there is no theory here, they don't really know why that is. So the CDC put out a prize, a $75,000 prize, I think, for someone who could develop a better system. And what did they come up with? Weather forecasting for the flu, pretty much literally. This, I love cases like this. The leader of the study was called Jeffrey Shaman, and they won the prize. And what they did was to take the FluTrans data and combine it with a model, a simulation model of disease spread. And they used the same techniques that are used in weather forecasting, data assimilation. That is, the model makes creates most of the data, and then it's corrected with observations as they come in. So, to try to wrap this up a little bit, how do we know what we know about climate change, about the Anthropocene? We have this long history of collecting data about the Earth and its systems. We have theories, physical theories about why things happen. We do a lot of modeling and simulation. There's an old infrastructure that's valuable because it means it's been through many, many rounds of testing and correction. There's a newer infrastructure for simulating the future, and that's what makes us nervous. We don't know how well we can rely on that, but the experiments I showed you are one way of getting to something like reproducible knowledge for simulation science. So that's this first paradigm, and this is a 20th century paradigm that crops up in almost any field where you're looking at large-scale environmental things. There are others, and toward the end of the 20th century, in science and technology studies and other fields, we start to hear a lot of phrases like mode 2 science, Pasteur's quadrant, other similar ideas about instead of doing sort of pure research, we should be focusing on problem-oriented science. There's been an idea floating around now for 20 plus years in the weather services and the National Oceanic and Atmospheric Administration for climate system services, which means that you would do climate services like weather forecasting. And that is actually being done right now with respect to short-term climate phenomena like El Nino. The political opposition to the concept of a longer-term climate system services has been so intense that you can barely even find this phrase, because once you say that you can that you can do this in a sort of infrastructural way, that ends the, from some people's point of view, ends the political debate and closes off the option of saying it's not happening. So there are other things too. I mean, I don't have a magic answer for what the best or for some perfect or new way of doing knowledge infrastructures for the future might be, but one of the ones I have looked at and really thought was very, very promising is there's a group based in Vienna doing what they call long-term socioeconomic research they have kind of taken a 2-century timescale approach to things that people have mostly studied over much shorter terms. And they'll do things like, they'll look at the Viennese farming in the 19th century, mostly very very sustainable, using a lot of animals, recycling the manure, recycling the stubble from crop harvests and everything else, but not very productive from a modern standpoint. Those same Viennese farmers then moved to Kansas, or some of them, in the middle of the 19th century, and they find their virgin land that has never been used for agriculture, and it is unbelievably productive. And their curve goes up, it just rockets upward. But of course, by the 1930s, what they've done is deplete all the nutrients, and they've created the Dust Bowl, and their productivity curve is plummeting. Meanwhile, the Viennese are still doing pretty much the same thing that they were in the 19th century. But in both cases, when you take it past that point, you get artificial fertilizer coming in, you expand the agricultural economy far beyond the local area, and so it starts to include shipping fertilizer and crops and harvests all over the world. And by the 70s or 80s, they look very, very similar. So it's one way of getting a handle on something that over a longer period than people usually do. There's, of course, the big data idea, the fourth paradigm, the concept that we can just do pattern matching on lots of data. There's citizen science, there's the publication of workflows, there are open access models, which of course are great, but also very problematic, in a lot of ways very expensive, without clear payoffs in many cases. And then I think what we can hope is that there will be new systems that combine all of these things and create new ways of closing loops, creating shorter time cycles between the creation of a problem and the solution of the problem, and building out from there. So I'll leave you with that, and the best idea for a climate change solution I've seen, the time machine, take us back to when we should have put a price on carbon. Better hurry. No, that's the great thing about this technology. Okay, thanks.
Thanks so much, Paul. So we'll open it up to questions, and I think we'll have Lara. If you want to ask a question, we'll have a microphone for you because it's being recorded. So you can open it up questions now, and we can.
Could you talk a little bit more about closing the loop and factories? That is something that you sort of mentioned briefly earlier, and how all of this data that's being captured from the environment might actually be used in that context.
Well, it's a thing I don't know a tremendous amount about, so I can't say a lot more than maybe. There might be other people in this room who have a better answer, and feel free to speak up if you do. But there are there are actually many concepts like that. The circular economy, life cycle analysis is another one where you try to create an estimate of the carbon impact or some other metric for what's going to happen over the whole course of a product's life. And that lets you compare things in a different way than you could without that information. So recently, I'm not going to remember the name of this website, but there's a new website that compares electric vehicles. And in fact, compares all kinds of vehicles in terms of their carbon footprints. And the answers are really very surprising. So first of all, it depends on where you live. If you live in a place where most of the electricity is made by coal, and you buy an electric car, you're actually going to make your carbon footprint worse, because you're going to be, it's the coal that will be producing that electricity. There are life cycle issues with respect to the manufacture of batteries and other parts of the car that sometimes make it, an electric car more polluting than a gas-powered car. Lots of examples like that. Factories, yeah, I don't think I can give you anything very precise about that.
Hey, love this talk, thank you. So one of my preoccupations is kind of with the intrinsic biases in algorithms and models, and I was thinking about this especially with that in the climate services, they're using these models, this huge database, most of the data is models, and this kind of feed forward that might reinforce existing biases. And I was wondering if you could talk a little bit more about how that might, hinder or detract from these knowledge infrastructures and their power, predictive power.
Yeah, well, of course, that's it's a big issue, and they're very aware of it. So there's a colossal amount of testing to find biases and diagnose them. Those graphs I showed. So, you see the biases in a little bit at least, in the bouncing around here. Some of that is variability that would be present in a natural system too, but you can also see that the variations are really, really large. So there's bias. But these data come from this thing called the Coupled Model Intercomparison Project. And my research project right now is to do a history of that project, which goes back to about 1988. The problem is that if you have simulations, lots of different simulations, and you're trying to simulate the future, how do you know which simulation is the best one? And the answer from these experiments has often been that, in fact, no individual model does as well as the average of many models. So in a lot of ways, it's kind of a crowdsourcing approach, but using simulations instead of human beings. The original name for this project, and the one that is still the kind of organization under which it works, is the Program for Climate Model Diagnosis. So what they're doing is they do these experiments in part to try to figure out why the models are producing the results they produce, especially the biases, and to try to correct them. So, the idea I have, which may or may not be true, is that in simulation science, there's no reproducibility as there is in experimental science, because you only have a simulation. What could you do instead? Well, you can make many models, especially, ideally, independently of each other, and then compare them.
Thank you for a wonderful talk. I was wondering if you could talk a little about censorship in terms of climate data. And, I've noticed, for example, like a difference in the reporting of, say, Hurricane Sandy to Hurricane Matthew. And, of course, this is sort of very much about media networks and things and probably outside your purview. But, now that we have satellites and sensors and they're international, particular countries, I imagine, can't just censor data. They might not try to put up a satellite again. How does it work from your perspective in terms of data, and if there's attempts to censor it?
That's a really interesting thing. So, putting my historian hat on, one of the fascinating pieces of meteorological history is that it's a form of international cooperation that has been incredibly robust. I mean, during the 2 world wars, communication was cut in a lot of cases, and the People's Republic of China, for a while, stopped releasing all its weather data. You can find weather maps from the late 1950s and early 60s where it's just a hole. There's nothing there, and the whole rest of the world is reporting. Very, very strange. But in general, most countries have participated in the reporting system even during wars. I mean, Cuba and the United States continued to share weather data during the Cuban Missile Crisis. There are lots of other examples like that. And part of the reason is that nobody actually benefits from censorship. Not only do the people who are not receiving data lose, so does the information that it doesn't report because it makes the forecasts less accurate. So it's kind of like the Postal Service. You have a huge incentive to keep cooperating and very little incentive to stop. So that's kind of the general case. But satellite data are really fascinating, and wow, there's a lot of politics around that. So one of the principal instruments for studying the climate is this thing called the microwave sounding unit that measures radiation put off by oxygen in the atmosphere at different levels. And for a long time, for about a decade, the only people who interpreted those data were these guys at the University of Alabama near the Space Center that runs the satellite. And they put out an interpretation of the lower troposphere data, the layer just above the ground where we live, that did not agree with all the rest of the climate trends. So all the weather balloons and the surface stations and everything else showed the climate warming, and they showed the climate cooling. So what happened was that another entity formed and began taking the raw satellite data and using their own algorithms to process them. Because satellite data are by far the most model-influenced data of any form that we have. Because what they're actually measuring is huge volumes of air, where almost everything else is measuring points or kind of lines as it passes through the atmosphere. So they have to turn these volumes into something that a model can use and figure out what layers are represented by which pieces of radiation and so on. So this other entity came into being, and they began creating their own version of the same data, and it disagreed, and they began to get the curve more in line with the radiosonde, the weather balloon data. And that has continued, and both of these groups still interpret it. The Alabama at Huntsville group is run by one guy who is a creationist, and major skeptic of climate models. So there is a certain political incentive, at least on his part. But what's happened is that both groups over time have released version after version of their data. And I think that's a trend you see everywhere, where there's no fixed, no permanently fixed data, only the kind of versions with newer and better, hopefully better algorithms. So censorship, I can't say anything about the weather reporting about the hurricanes.
Yeah, a hard question to respond to, because it has to do more with the networks that are reporting in, what the internal politics are.
Yeah.
So I have a question here. I'm not sure you can answer this, but I'm just curious about your thoughts, because one of the implications, and I'm thinking of Bernard's talk yesterday too, about the way that you position kind of the epistemology of the simulation of the model, is clearly to generate these futures that however accurate they might be, you can't be accurate about the future really, because the point of the model of the simulation is in some ways to change the future. But what was interesting to me is that, and it's always interesting that it seems like the models are terrible, and that the actions are very unresponsive. But I found that point about the locality of climate maybe one of the clues to that. And I don't know if you can answer that, but whether you've thought about how, like when I thought about your Michigan getting to be like Washington, you said it wouldn't be that great, but it wouldn't be that bad either. In some ways, if you think about catastrophe that we're hearing about. So I'm just wondering if you have any thoughts on that, or just something we might pick up in the panel that just struck me as an interesting juxtaposition of the local and also the kind of call to action on a global scale, which is very difficult to enact.
Yeah. Well, of course, there's so many issues like this where our biggest problem is that we are built to respond to short-term stimuli. The thing that if a bird comes flying into this room, everyone will look at it. You cannot not look. And that's what always happens. We're distracted by the closest, most salient extreme. Climate is a catastrophe. Climate change is a catastrophe, but it's happening on a time scale that we don't really perceive. So things like that, the 135 years and 29 seconds are amazingly good at kind of showing a process that is very hard to see when you just live in it. If you go live on the time scale. There's Another great project like that is called the Extreme Ice Survey. Anybody seen that? They were showing this on screens in the train system in the Denver, Colorado airport. You'd be waiting for the train on the screen. What they have are stop-action cameras aimed at glaciers all over the world. They did it with 95 glaciers. And these guys are actually astonished by what they found because they ran this project for about 5 years, and they had to keep going back and moving the cameras because the glaciers are melting so fast that they recede out of view. So, and then they just play these back, at kind of 1 frame a day, and you see the thing just dissolving. It's such a different experience from anything that you can have by standing there looking at a glacier, even though you might know that the glacier used to be in a different place. So, I think one thing that you can do with data is to create these different times that people have a very hard time perceiving. That's certainly useful.
Hi, thank you very much for this great talk. And I just had a question about, in a sense, what's activating this monitoring, modeling, and memory infrastructure. So I was wondering how this technosphere and technometabolism will look like from the perspective of energy production, and in a sense labor is one of the things that produces energy, especially for concerns two aspects, two slides in particular were very striking. One was the circular economy and the UPS sort of system, where clearly the person that is driving is a little, the labor in a sense involved is a little bit squeezed in that system. But also the image of the nuclear test, where the whole point was to get not just a destructive force, but also some energy beyond, much more productive in a sense than traditional forms of energy. So I'm wondering how energy and labor sort of would fit into this future techno-metabolism. Because that's ultimately what is activating this infrastructure. Your example of the car the electric car that would consume more in a place where energy is produced by coal, I think was very, that was a crucial example of that. Thank you.
That is a great question, but I'm not sure I know what to say to it. One way to think about it is that there are, the whole fossil fuel infrastructure is based on really dirty work. It's horrible work. Mining coal, being on an oil rig, working with natural gas and all the pollutants that come out of the ground near the fracking sites. As a form of labor, if that were the only thing that you thought about, you would never do it. So, of course, a lot of what's happened over time is the automation of some of that work, but there's still very little of it that doesn't involve people getting hurt, being dirty and polluting their lungs and everything else. I'm not sure what else to say about that, but let's move on. We can talk about this tomorrow when I see you.
Great, so I think we're going to stop the questions now because we have a panel after a coffee break. So I invite you outside for coffee. We'll have a panel with Bernard Stiegler and Paul Edwards and Professor Jennifer All from the iSchool. So let's take a break and first thank Paul for such a great presentation.